Hello, welcome to Basics of Finite Element Method Part 2. This is the second week for this particular course, and today is the second day of this particular week. Yesterday, we discussed different types of errors which are there in FEA solution relative to the exact solution. And what we had discussed and explained were that there are principally three different types of errors which exist in any finite element analysis solution. The first type of error which is there in FEA solution is domain approximation error, and that particular error is not present in 1D problems, but it does exist in 2D and 3D problems, because if we have to use straight edged or straight faced elements, we cannot exactly replicate the geometry of a curved 2D or a 3D object. So, because of this, there is this domain approximation error which creeps into the finite element solution. The second error which is there is known as approximation error, and this creeps in because we assume a particular function to represent the variation of unknown variables over the domain, and if this approximation function is not exact replica of the actual function, then there will be this approximation error, and this error can be reduced by increasing the order of approximation function, especially if we are using polynomial functions to represent this variation of variables over the domain. And the third error is computational in nature, and it is inherent in any algorithm where we are adding, subtracting, dividing, taking square roots and doing several mathematical operations. So, it depends on the accuracy of our calculations and also the accuracy of the quadrature method which is used to integrate to perform computational or numerical integrations. So, three errors: domain approximation error, then polynomial approximation error, and the third one is quadrature and finite arithmetic error. What we will do today is discuss how can we measure and quantify these errors, and there are several ways to measure these errors. So, that is what we are going to discuss today: measures of errors. So, we will again explain these measures in context of a problem. So, suppose this is the domain and it is a one dimensional domain, and here x is equal to a and here x is equal to b along the x axis, and there is some variable at any point p, and this variable is u. So, we want to know what is the value of u for different locations of p. So, basically our aim is to find u as a function of x. Okay. Now, this u x could have two solutions. One is exact solution, and I call this exact solution as u of x. Okay. And then there is another solution, and this is inexact solution, FEA solution, and by nature finite element solution is inexact. And I call this finite element solution as u h, and this is also a function of x, and x varies from x is equal to a to x is equal to b. Okay. So, we have two solutions. One is the exact solution which is u of x, and the other solution is inexact solution which is u as a function u h as a function of x. So, the first measure is called, so first measure measure 1, it could be point-wise error. Okay. And I call this EP, and this is a function of x itself. So, what is this point-wise error? It is just the difference between u, the exact solution, minus the FE solution. Okay. So, that is my point-wise error. So, what does it mean? That from point to point, the value of this error will change. From point to point, the value of this error is going to change. Now, an important thing to note about this is that using this function EPX, I do not have a single number. See, EP is a function. So, I cannot say that error is 1% or 2%, because this is a function. So, this number will change from point to point. So, I cannot assign a single value. So, I cannot compare two solutions, because this is not one single number. So, in that context, we will discuss another measure, measure 2, and this is called max norm, maximum norm, and some people also call it SUPMET, submetric. Okay. And this is expressed as, so this is a format in which it is written. So, this is u minus UH. So, I am just omitting the x, but u is a function of x and UH is a function of x. Just for purposes of brevity, I am dropping out the x. And this, so this is the max norm, and what is it? It is equal to maximum value of the absolute, maximum value of absolute value of u of x minus UH of x. So, this is the max norm, and here x ranges between B and A. So, this is, so first thing is that this is a positive number, because it is an absolute value and it is the maximum possible value of this difference. Okay. So, for instance, if I have so this is x, this is x axis, this is A, this is B. Let us say this is the exact solution. So, this is exact, and I am interested only between A and B domains, and this is the inexact solution. So, suppose I am having two elements and I am using linear interpolation. So, this is the inexact, this is blue is FE solution. So, the difference between the exact and the inexact, the exact and the inexact solution is maximum at this location. So, this is max norm. At this location difference is 0, at this location difference is 0, at this location difference is 0, difference keeps on increasing and it becomes maximum at this location, right, and at all other locations this difference is less compared to this maximum value. So, this is defined as the max norm or submit. So, this is the second number for quantifying the type of or the magnitude of error. max norm. Then there is a third measure, and this is called energy norm. And oh, I forgot to mention that here there is a subscript which is infinity. So, this is how it is designated. Okay. Two parallel bars, then you write u minus uh, and then another two parallel bars, and then you put a subscript infinity. Now, this energy norm is written as u minus uh, and here the subscript is m. So, m designates energy norm, m designates energy norm, and this, if I have to calculate it, it is a little complicated formula, and the relation for this is excuse me. So, this is the expression. So, it is a little complicated, but we will explain this. So, first thing is that it is a summation of first thing is, oh, so this is integrated over x is equal to a to x is equal to b. So, first thing is this energy norm is an integral, and because it is integrated over the domain a to b, and because it is integrated, it is still a single number. And then what do we integrate? We integrate a series of terms where this series is an additive series, and this I changes from 0 to m. What is m? We will discuss that. But so this is I changes from 0 to m, and then you take absolute magnitude of derivatives of u and derivatives of uh, right, and it is not just first derivative, it could be second derivative, third derivative, whatever. So, it is derivatives of u and derivatives of h, you take the difference, square it, integrate it, and then take the square root. That is what gives you energy norm. Okay. Now, what is m? M, 2m corresponds to order of differential equation. 2m represents order of differential equation. For instance, the bar equation is example, bar equation, where we have a bar under tension. The equation for this is minus d over dx a du over dx equals f. So, this is a second order differential equation. So, this second order differential equation means that m is 1, m is 1. In beams, especially Euler-Bernoulli beam, it is a fourth order differential equation. So, in that case m will be 2. So, if I have to find a max norm for this second order differential equation, m will be 1. So, I will range from 0 to 1. So, first we will have d0 u over dx 0, which means u itself, right. 0th order derivative of any function is the function itself, and then it will also include first order derivatives. Okay. So, it will include u and u prime. If I go to beams, it will include u, u prime, u double prime, it will go up to that, right. So and so on and so forth. Okay. So, this is how we generate energy norm, And the reason it is known as energy norm is that here we have squares of derivatives involved in the calculation of the norm. And when you look at, especially for elasticity problems, when you calculate the energy of the system, that also involves squares of derivatives. For instance, strain energy is E, which is Young's modulus times strain square divided by 2. So, that is the strain energy density. So, here we are the norm computation of norm involves derivatives of U's and squares of derivatives of U's, and that is why it is called energy norm. Okay. So, this is the third measure, and the fourth measure is called L2 norm, and this is written as U minus UH. Again, on both sides we put two parallel bars, and here we put a subscript O. Okay. So, that is an energy norm. You take the whole thing and then take the square root of that. Oh, excuse me, I put this bracket here. So, this bracket should be here. Okay. So, this is important, yeah. So, the L2 norm, this is defined as integral of A to B U minus UH, and then you take the absolute magnitude, square it, and then integrate it, and you take the square root of the integral. So, that is the L2 norm. Now, this L2 norm, if you look at, it represents the area, the difference in areas, right. So, what is this u times dx is what? The area under the curve u. If you integrate u times dx, if you integrate u with respect to x, then the integral will represent the area under the curve for u. Similarly, integral of UH times dx will be area under the curve for UH, right. So, this norm, it represents the difference in the areas under. So, this is somewhat tells us about energy, this tells somewhat about difference in areas. So, to give you an illustration, so this is x, and here I am plotting u and UH. Okay. So, let us say this is my u, this is u, and I am plotting it. Let us say this is x is equal to b, and this is x equals a. So, this is u of x, this is exact. Okay. Next, what I am going to plot is so this green line is the Fe solution, which is UH. So, what you see is that I have broken the domain for FEA into how many parts? 4 parts, and I am using interpolation function which is linear, right. So, this is UH H of x, right. So, my max norm is this difference, this is max norm, because the difference is maximum at this point. And my L2 norm is this red area. it is this red area. So, if I add up all these red areas and add them up, that is my L2 norm, and max norm is the maximum difference which is shown here. Energy norm I cannot so easily depict it on this graph. In that case, I have to plot energies and then somehow normalize it, and then I will be able to plot the energy norm. So, these are 4 different measures to quantify how accurate our solution is. The first measure is pointwise error, right, and it is actually a function. So, it is not a measure, it is not a single number. So, we do not call it a measure, even though in this discussion we have called it a measure, but it is a function, it is not a single number. And the second measure is max norm or submetric, and here the way we find it out is that over the domain we find the difference between the exact solution and the FE solution, and wherever that the maximum value of that difference, absolute value of maximum, the maximum value of absolute value of difference is defined as max norm. In energy norm, we compute the differences in derivatives and then square them, these differences, take the absolute value, square them, integrate this over the domain and take the square root, and that is how we calculate the energy norm. And finally, there is this L2 norm, which represents the difference in areas under the exact and inexact solution curves, and here it is basically u minus un, the absolute value of that, you square it and then integrate it over the domain and take square root. Now, all these norms are, we have discussed, are in context of single variable 1D situations, but we can extend the same logic for multi variable problems and also multi dimensions. So, in case of if the domain is 2D, then we just do not integrate it over x, but we integrate it over x and y. Okay. If the domain is 3D, then we integrate it on all the 3 domains. And then when we are calculating norms, we are taking differences. So, again if there are 2 variables u and v, then we take u minus uh, and then also we do v minus vh. So, like that we calculate these norms, but we still end up with one single number. So, specifically 3 important metrics or measures are there: max norm, energy norm and L2 norm. And then of course, there is a pointwise error function also, and that is basically the difference between exact solution and the inexact solution. So, this completes our discussion for today, and we will continue this discussion tomorrow. What we are going to do tomorrow is we will start talking about convergence and how finite element solutions converge and on what parameters they depend on and to what extent. So, thanks a lot, and look forward to seeing you tomorrow. Bye.